Hello and welcome to Chemistry 103, and today we are going to start chapter 4 in this course. And I will start this chapter by showing you this picture. This is the same lamp connected to the same battery. So consider this is the same lamp connected to the same battery, but sometimes it's so in the first instance it's on, and the second one is kind of dimmed, it's half, and the third one is off. If you are wondering why this is happening, as you might know, this goes all back to the solution that this lamp is inserted on. Okay, so this is what the chapter is talking about. The chapter is talking about solutions and electrolytes, and very soon we are going to define these two terms. Some solutions like sodium chloride in water will conduct electricity, and that's why it's called an electrolyte, and this might be the solution in the picture to the left. Some solutions, they do not conduct electricity because of the fact that there are no ions in them. There's just in the case of pure water. So this chapter will talk about general properties of aqueous solutions, and we will also talk about precipitation reactions and acid-base reactions, and this is where the first exam is up to. So the first exam is up to section 4.3. So acids and bases are included in the exam. So the rest of the chapter will talk about oxidation reduction reactions and concept of concentration and acid-base reactions. Now, before we go further on, we need to define what is a solution. A solution basically is a solute and a solvent. It's a homogeneous mixture of two or more substances made of a solute and a solvent. And this is the difference between a mixture and a solution. A mixture would be a heterogeneous mixture of two things. So when you add, let's say, sodium chloride in water, the sodium chloride will dissolve, and that will form a solution. But when you mix, let's say, sand and water, the sand won't dissolve in water, and that will make you a mixture. So the solute is a substance present in a smaller amount, and the solvent is the substance present in a larger amount. And this is important for you to understand that water is not always the solvent. So if I take, let's say, 80 ml of water and I add 20 ml of ethanol, water in that case will be the solvent. But if I reverse this idea and I got, let's say, 80 ml of ethanol and I add 20 ml of water, in that case the solvent is the ethanol. The solution is not only a solid liquid solution, just like NaCl or KBr or sugar and water. The solution can be any combination of a solid, liquid, and gas. So you have liquid solution, just like the ethanol water. You have solid liquid solution, like sugar and water or salt and water. You have also air solution, which is air itself. It's a mixture of gases. You have also the other combinations like I will say liquid gas. That would be a soft drink. The Coca-Cola or the 7-Up would be a liquid gas because it contains water and CO2 gas, carbon dioxide. There is also solid solutions, which are alloys. An example is the solder, which is made of tin and lead, and the one that is showed in the picture here. There's also, of course, other types of alloys. There is bronze and other types of alloys that they are considered as solid solutions. Now we move on to classify materials or solutions into two categories: electrolytes and non-electrolytes. The word electrolyte means a solution that conducts electricity, and a non-electrolyte, that would be something that would not conduct electricity because there are no ions on it. Don't mix up the idea of solvations with electrolyte and non-electrolytes. There are materials that they do dissolve in water, like sugar, okay, but they are not electrolytes. So sugar does dissolve in water, but doesn't mean it's electrolyte. It's non-electrolyte. So an electrolyte is a substance that, when dissolved in water, results in a solution that conducts electricity, and a non-electrolyte is basically a substance that, when dissolves, results in a solution that does not conduct electricity because there are no ions on it. Now, why electrolyte conducts electricity? Well, you know that before. NaCl solid, when you put it in water, it's going to form Na plus ions plus Cl minus ions, and these ions can transfer the charge from one electrode to the other, or one side of the battery, I will say, to the other side, and that will allow the electrons to move in the circuit. and that's why an NaCl solution is an electrolyte. There's also something called a weak electrolyte, which is an example of that would be vinegar, which is acetic acid. Acetic acid is a weak acid, so when you put it in water, it will ionize to acetate ions, CH3CO- and the H plus ions. But these two ions, they combine again to form acetic acid. So the formation of these ions is not complete, and this is called partial ionization or partial dissociation of acetic acid. And this is an example of a reversible reaction. So these two arrows means we have a reaction in both sides. Okay, and here we have a scenario or a situation where you have a weak acid, a weak electrolyte, because the ionization is incomplete. Now, moving on to the idea of a non-electrolyte, an example of that is sugar or glucose. So glucose does actually dissolve in water. It will form glucose aqueous, but there are no ions formed. This is not ionic compound. This is an organic compound. When you put it in water, it will dissolve. Water will surround these molecules. Okay, it will let them dissolve, but there are no ions involved, and therefore that's not considered a weak electrolyte. So here's a table of the examples of strong, weak, and non-electrolytes. Strong electrolytes, the examples of that is all strong acids, such as HCl, nitric acid, and sulfuric acid. Also perchloric acid is a very strong acid, it's a strong electrolyte. Also all the strong bases, like sodium hydroxide, KOH, PaOH2, all of that. And also all the ionic compounds that dissolves in water, and that's important for you to understand. So for example, NaCl does dissolve in water, and that's why it is a strong electrolyte. But calcium carbonate, for example, as we are going to know in a few seconds, calcium carbonate, which is a chalk, does not dissolve in water, and therefore it is not an electrolyte. It's not a strong electrolyte, although it's an ionic compound. So not all ionic compounds they are strong electrolytes, only those who dissolves in water. The weak electrolytes are all the weak acids, and just like HF, HNO2, and acetic acid, of course, and ammonia, which is a weak base, and all ammonia derivatives, they are considered as weak electrolytes, and the H2O plus ions, and water itself. So non-electrolyte examples are the glucose and their family, glucose, fructose. Alcohols like methanol and ethanol, these people, they dissolve in water, but they do not form any ions, and urea. Here I need you to draw your attention to this. You need to memorize the 6 strong acids. They are basically sulfuric, nitric, and perchloric, HCl, HBr, HI. These are the 6 strong acids that you need to keep in mind for the rest of this course, okay? Those are not the complete list, but this is the stuff that you need to put your mind, remember all the time that these are strong acids. Everything else should be weak. Some people consider HClO3 also to be strong, and there are, of course, there are some other strong acids in the organic chemistry, but here we just remember these 6 for now. Having said that, when I say HNO3, that's strong, but HNO2, which is nitrous acid, that's weak. When I say HCl, HBr, HI, those are strong acids. So where is HF? HF is not strong. HF is weak acid. When I say H2SO4 is a strong acid, which is sulfuric acid. H2SO3, which is sulfurous acid, that's a weak acid, and so on. Okay? So you can watch this YouTube video on how water actually is able to dissolve these ionic compounds and organic compounds by a process called hydration. Hydration is the process in which an ion is surrounded by water molecules that is arranged in a specific manner. This is very important that you watch this YouTube video and understand the hydration process. Now we need to move on to precipitation reactions. So the question is, why sodium chloride dissolves in water, but stuff like silver chloride, for example, or calcium carbonate, they do not dissolve? That's the idea of precipitation reactions. There are some stuff that you, when add in water, they don't dissolve basically, and they form what we call a precipitate. A precipitate is that solid that accumulate at the bottom of the tube And this is another YouTube video. I want you please to take a look at it and see how beautiful the formation of that precipitate. So here we are considering adding two substances, lead nitrate and sodium iodide. They are both soluble in water. Okay, so they dissolve in water, and actually they look like water. So a solution of lead nitrate will look colorless. Okay, it has no color. And sodium iodide has also no color. And I refer to them here by the words, by the letters AQ. That means aqueous, indicating that these are soluble in water. So when you add these two things, you observe some kind of cloudy yellow solid forming. Okay, and that's the lead iodide PPI2 that you observe. And I want you again, please, to watch that YouTube video in the previous slide to see how beautiful is that forming. There is other product which is NaNO3 aqueous. That's soluble in water, so you wouldn't see it. You will only see the PPI2. So if you wait for this a few seconds or few minutes, all that yellow solid will accumulate at the bottom of this tube, and that's what we call a precipitate. Okay, a precipitate is that. Now the question is how to predict whether a precipitate will form or not. So that's why we have something called the solubility rules. Okay, the solubility rules are here. They are arranged in this table, and you need to memorize this table. Okay, and I have organized this table back again into this slide to just make it easier for you. So now this slide separates or classify ions and cations into cations and anions into soluble or insoluble. So we start with the soluble ones, the green ones. So all group 1, lithium, sodium, potassium and rubidium ions and cesium ions, they are all dissolved in water. Okay, also all the halogens, the Cl minus, Br minus and I minus, not the F minus, the Cl minus and Br minus and I minus, they are soluble. And that's why NaCl is soluble, because it contains Na plus and ACl minus, and they are both soluble. So that's, you see, it's easy. Also ammonium plus, anything that contains ammonium. Also ammonium, anything that contains ammonium is soluble. NH4 plus. All nitrates are soluble. So that's why you see in the previous example why NaNO3 is soluble, without any exceptions. Acetate and also bicarbonates are soluble. Okay. Chlorates, perchlorates are soluble. Sulfates, they're soluble, but there are some exceptions. Cl minus, Br minus, and I minus, but there are exceptions for this. You have to see the stars. When I say Cl minus is soluble, that means it's soluble except halides of Ag plus, Hg22 plus, and pp2 plus. So NaCl is soluble, but AgCl is not, because it contains Ag plus. The insoluble stuff contains carbonates, chromates, hydroxides, phosphates and sulfides. But this is confusing now, because NaOH, sodium hydroxide, is soluble. So now how comes it is insoluble here? Well, there are exceptions. It says here that all hydroxides are insoluble except two stars, except of group 1 and Ba2 plus. So NaOH contains group 1 with the OH minus, and that's why it is soluble. Now this is a picture of some precipitates that you might see in the lab. We have cadmium sulfide, lead sulfide, nickel hydroxide and aluminum hydroxide. These are beautiful colors, and now I want you please to think why these materials are not soluble based on the solubility rules. So now let's apply these solubility rules to predict if these compounds here that we have as an examples are soluble in water or not. So the way I do this is, for example, for the KBr, I break this down into its ions. I know KBr, when you put it in water, it should give K plus and Br minus ions. Okay. Now there is a rule that says K plus is always soluble. So give this a check mark with no exceptions. And the Br minus is soluble, but there are exceptions. There is a star except of Ag plus and the mercury and the B. So there is nothing like that here. So this should be soluble, and I expect in this case that Br is soluble in water. Okay, so this is soluble in water. CaCO3 is insoluble, and the reason for that is that CaCO3 contains Ca2 plus ions if it dissolves in water, and CO3O2 minus Carbonates are a big problem. Carbonates are insoluble in water, except group 1. But this is not group 1. This is not group 1 neither ammonium. Okay? So this is insoluble. The exception does not apply here. So this would be insoluble compound in water. So the idea here is you figure out which ions has a rule and you apply the rule, and please do not make your own rules. There is no rule here that says calcium 2 plus is not soluble. If you take a look at this table, there is absolutely no rule in this boxes says that calcium 2 plus is insoluble or non-soluble. So you have to go to carbonates. Carbonate says it's insoluble except group 1 and ammonium, so it is insoluble. NaHCO3 is the bicarbonate. It's the stuff that it's the baking soda, the stuff you use to make cakes. Let's see if this is soluble or not. Now this one should be made of Na plus and HCO3 minus. I have a rule that says Na plus is soluble. Do we have a rule for bicarbonates? Yeah, we have it. See, it's HCO3 minus is soluble and with not even exceptions. So that's why bicarbonate, when you want to make cake, it's easy to dissolve in water. KNO3. There is a rule that says nitrates are all soluble, and that makes it easy for you. Okay, so NO3, anything that contains NO3 should be soluble in this way, and also K plus is soluble without exception, so this should be good. NH4OH. Okay, we have a hydroxide here, so let's see what's going on. Do you expect NH4OH to be soluble or not? NH4 plus and OH minus. So hydroxides are insoluble in water. Okay, hydroxides are insoluble in water, but there is an exception says that except if they come with group 1 and ammonium. So this one is insoluble, but ammonium would give it a green light. Okay, the existence of ammonium with the hydroxide will make this compound soluble, and therefore this is soluble in water. Copper 2 phosphate. Well, what is copper 2 phosphate? I know copper 2 is Cu2 plus. I know phosphate is PO4 3 minus. When you apply the cross multiplication rule here, you obtain that this is Cu3 PO4 all 2. This is what copper phosphate. Now the question if this is soluble or not. I know there is a rule about phosphate that says it is insoluble, and I have to check the exceptions. Phosphates are insoluble except 1 star if they come with group 1 or ammonium. Copper is neither group 1 or ammonium, so this should be insoluble in water. So that's if you apply the rule, you will find it to be easy. So now we move on to explain the difference between molecular ionic and net ionic equations. Now, this is an example of a molecular equation, okay? Where you have lead nitrate, it should be soluble in water because of the existence of nitrates. If it reacts with NaI, again it's aqueous because it's Na and I minus. And now you see how beautiful and how easy is this now to expect or predict the solubility of these things. This will lead to PPI2, which is solid. Now you want to ask yourself why it is. You can go back to the solubility rule, and you will find there is a rule that says I minus is soluble except if it comes with PP. Okay, so this is the solid that precipitate that you are forming plus 2 NaNO3. This is called a molecular equation because it contains molecules. Now I want to write the net ionic equation of that. So the first thing, I want to make sure that this equation is balanced and it looks balanced. The other thing, I want to break this down into its ions. I know PPNO3 2 is 2 PP ions. It's PP2 plus ions plus 2 NO3 minus ions. The 2 NaI, that's 2 Na plus and plus 2 I minus ions. The PPI2 solid does not dissolve in water anyway, so we cannot break it into ions, and that's why we move it down as is. And you see here in the second equation, it is written as is PPI2 solid. NaNO3, it dissolves in water, it's an aqueous. So we break it down to 2 Na plus 2 NO3 minus. Remember that 2, the prefix before the NaO, it's multiplied by the sodium and the nitrate. This is called an ionic equation because it contains ions. And if you look at this equation, you will find that there are something shared in the left and right. The Na plus appears in the left and also appears in the right of the equation. And this is called the spectator ion, just like these people watching this game, football game. These are called spectators. So there are the real players. In this case, they are the pp2 plus and the 2i minus. Okay, and the ppi2 solid. But the Na plus and the NO3, they are just the spectators. They're just watching. Okay, so we cancel them out from the ion equation, and the net ion equation would be pp2 plus 2i minus forms ppi2 solid. That's what is really going on in this reaction. Okay, that's the net ion equation. So for this question, we are going to practice it in class. So thank you for listening and have a great day. Thank you so much.